Welcome to the deep dive. Now, if you're listening, you almost certainly know about the Big Bang model. It's the standard story of our universe, right?
Sure.
Explains the cosmic microwave background, element formation. I mean, it's been incredibly successful.
Oh, absolutely. It's a cornerstone. And yet, ask any theoretical physicist about its biggest weak spot.
And they'll point right to the beginning, to time equals 0.
Exactly. That initial moment, the supposed start of everything. It's where general relativity, our best theory of gravity, just throws its hands up.
Yeah, it predicts this point of infinite density, infinite temperature, the singularity.
Which is basically math code for Houston, we have a problem.
Mm.
It means the theory itself is broken down. It can't describe that state.
It really forces this massive question, doesn't it?
Yeah.
A really fundamental one. Can we actually forget the Big Bang? Is it possible the universe really has no beginning?
That's the core of it. And that's what we're diving into today. There's this really interesting new mathematical framework emerging.
The Quantum-Unified Vacuum Theorem, or Qμν, as we'll probably call it.
Right, QUV, or Qμν. And its central idea, its core thesis, is pretty radical. It suggests that this Qμν theory mathematically removes the Big Bang singularity altogether.
Removes it, not just pushes it back or smooths it out.
No, it replaces it. It swaps that whole concept of a starting point for an eternal cosmic cycle, a self-regulating one.
Okay, self-regulating how? What's driving it?
Well, this is the key part. It's driven by the dynamics of quantum entanglement entropy and a really deep underlying fractal structure to space-time itself.
Wow. Okay, so geometry isn't just the stage, it's part of the play. It's emerging from quantum information.
That's the claim. Geometry is an expression of quantum information.
So our mission today is clear. We need to figure out how these entropic corrections, you call them, how they provide some kind of repulsive force, something to stop that infinite crunch at the Planck scale.
Exactly. How does the math prevent the universe from ever hitting time equals 0? That's the goal. It's a huge claim, so yeah, we need to really unpack the mathematics behind it.
Okay, let's start with the problem itself. Classical gravity, general relativity.
Right. GR describes gravity beautifully as space-time curvature. Mass and energy tells space-time how to curve, and curvature tells mass and energy how to move. Simple, elegant.
But run the movie backwards.
And everything gets closer, denser, the curvature ramps up exponentially. And at that theoretical TO point, infinity, the curvature becomes infinite.
And the basic equation, Gμ equals 8 pi g over c⁴ times Tμ, it just breaks. It can't handle infinite density. Space-time itself just stops making sense in the equations.
Precisely. And GR gives us absolutely nothing to stop that collapse. Not for the universe, not inside a black hole. It just signals error, non-physical result.
Okay, so Qμ theory steps in here. What's the fix?
It modifies the fundamental Einstein field equations. It says, okay, the geometry side, Gμ, and the cosmological constant term, lambda Gμ. That's fine. But the source side needs an addition.
The right side of the equation, the stuff that causes gravity.
Exactly. We still have Tμ, the classical stress energy tensor. That's mass, energy, pressure, momentum, all that stuff.
But Qμ adds something else.
It adds a crucial quantum correction term. We call it Qμ, the entanglement correction tensor. So the full equation looks like Gμ plus lambda Gμ equals 8pg over c⁴ times brackets Tμ plus this Qμ term.
Okay, hold on. So geometry, the left side, isn't just responding to normal mass and energy anymore.
Correct. It's also responding to the energy density that's inherent in quantum information, in the entanglement entropy of the system.
So the way quantum bits are connected, their entanglement, that now directly influences gravity.
That's the core idea. Geometry and quantum correlations are now fundamentally linked. One influences the other directly.
But how does information create a force, and a repulsive force strong enough to counteract gravity, especially near a singularity? That seems like a leap.
It does, but we need to look inside that Qμ tensor. What's it made of? Two parts are really critical for avoiding singularities, and they become important exactly when things get incredibly dense.
Okay. What's the first part?
The first is what we call the alpha term. It represents a coupling between curvature and thermal energy. Mathematically, it's alpha times this combination involving the Ricci tensor and the stress energy tensor. And it's linked locally to something called the Unruh temperature.
Unruh temperature. That's the weird effect where if you accelerate, even in empty space, you perceive heat, right? Like space-time itself is warming up relative to you.
Exactly that. The faster the acceleration, the higher the perceived temperature. The alpha term basically builds this effect into gravity itself.
So near a singularity where space-time is incredibly curved.
Which involves involves immense gravitational acceleration. The theory says this generates local thermal energy right out of the vacuum's quantum structure.
And that thermal energy feeds back into the gravitational field, a loop between geometry and quantum heat.
Precisely, a feedback loop.
Okay, interesting. But wouldn't adding thermal energy just add to the density? Make the collapse worse, maybe? Where's the pushback?
Good question. That comes from the second component, which is arguably the powerhouse here, the beta term, the entropic gradient stress.
Entropic gradient stress. Okay, that sounds significant.
It is. It's represented by beta times Boltzmann's constant, K(b), times terms involving the gradients, the rate of change of entanglement entropy S.
So not the entropy itself, but how fast the entropy is changing from place to place.
Exactly. This term treats that change, that gradient in informational disorder, as a real physical stress, a dynamical force.
A force from information flow. Can you give an analogy? Because entropic gradient stress is a bit abstract.
Okay, think of it like trying to compress information itself beyond a certain limit. As you crush matter towards a potential singularity, the quantum entanglement in that tiny region becomes insanely dense.
Right. Everything is interacting with everything else nearby.
So the informational disorder, the entropy S, is shooting towards its maximum possible value, and its gradient, how sharply it's changing right at that boundary, becomes enormous.
Okay.
The beta term says that this extreme informational pressure translates directly into a physical outward pushing force, like the universe resisting being compressed into an infinitely small informational point.
Almost like an information pressure pushing back.
That's a good way to think about it. It acts like an anti-gravity effect, but it's sourced by information, not exotic matter. It effectively creates a repulsive bubble right at the Planck scale, physically preventing infinite collapse.
That's elegant, actually. But theoretical elegance isn't proof. How can we test this? We can't exactly rewind the universe.
No, but we can look at places where gravity tries to create singularities now. Black holes.
Ah, the local version of the cosmic crunch?
Exactly. And this is where Qμ makes a concrete, potentially testable prediction. It states very clearly that black hole evaporation Hawking radiation does not end in a classical singularity.
So the black hole doesn't just evaporate down to nothing, to a point.
Correct. The entropic repulsion, that beta term force, kicks in before it reaches zero size. It halts the collapse.
And leaves what?
It leaves a stable, zero-temperature remnant, a tiny fundamental nugget of highly compressed quantum information. We call it a black hole remnant, or BHR.
Okay, a remnant. Does the theory predict anything about it? Like its mass?
It does, and this is crucial. It predicts a very specific mass. It's tied directly to the theory's fractal foundation. The remnant mass, M remnant, is predicted to be the Planck mass divided by the square root of the system's fundamental fractal dimension, d sub f.
D sub f, we'll need to get into that. But there's a number.
Yes, when you plug in the value for d sub f derived from the theory, the remnant mass comes out to roughly 0.726 times the Planck mass.
0.726 Planck masses. That's incredibly specific. Not just small, but that value.
Exactly. It's a hard prediction.
So the implication. If we could somehow prove that evaporating black holes stabilize at exactly this mass,
then the extrapolation is unavoidable. If the Qμ physics prevents the local singularity inside a black hole, the same physics, driven by the same entropic repulsion, must have prevented the global cosmological singularity.
the universe never reached T0.
Yeah.
It bounced or transitioned from an earlier ultra-dense state, stabilized by this information pressure.
That's the consequence. No Big Bang singularity, an eternal cycle.
Okay, to really buy into this eternal cycle, we need to tackle that philosophical shift you mentioned. This idea that geometry, space-time itself, isn't the fundamental thing. That's a huge departure from GR.
It is. It's really embracing the if from qubit idea, but giving it mathematical legs. The Qμ framework suggests space-time dimensions, distance, curvature isn't the stage, it's emergent.
Emergent from what then?
From an underlying structure of pure quantum information. Think of reality at its base level, not as smooth space, but as a vast interconnected network of, well, think of them like abstract qubits, entangled qubits.
So when we perceive space-time curving, that's just the large-scale effect of how densely those qubits are entangled.
You've got it. More entanglement in a region corresponds to what we perceive as stronger gravitational curvature. The theory even writes this down in what's called the entanglement Hamiltonian, H sub E.
Okay, what does that show?
It explicitly links the discrete version of Ricci curvature R line directly to the interaction strength between these conceptual qubits. It involves terms coupling curvature to things called Pauli operators, which describe the quantum state correlations.
So literally the math says geometry is the pattern of quantum correlation.
Yes. Where the entanglement is dense and complex, space-time appears curved. The geometry is the information structure made manifest.
That paints a picture of reality built on self-similar patterns, where the rules of information are maybe the same at all scales. Does the theory capture this self-similarity?
It does, and it leads to what I think is maybe the most fascinating constant to come out of Qmnu theory, the Hausdorff fractal dimension, d sub s.
A fractal dimension for space-time, what's the value?
The mathematics of the theory fixes it. It has to be log base 3 of 8, or log 8 over log 3, which is approximately 1.8928.
1.8928. Okay, that's weird. It's not 3 spatial dimensions, not 4 space-time dimensions, not the 10 or 11 you hear about in string theory. What does a dimension of almost 2 mean at the smallest scales?
It means that if you could zoom in way past the scales we can currently probe, space-time, according to Qmnu, wouldn't look smooth. It would look like a complex, structured network, mathematically behaving like something just under two-dimensional, like a very intricate surface.
Characteristic of entanglement patterns, maybe?
Exactly. And as you zoom out, this fractal structure builds on itself, and the effective dimension smoothly increases.
Yeah.
It flows from this near 2D structure at the Planck scale up towards the 4D space-time we experience macroscopically.
And this dimensional flow, does it do anything useful?
It's absolutely crucial. It's the key to what's called asymptotic safety.
Asymptotic safety, that's a big deal in quantum gravity research, right? The idea that a theory could remain well-behaved, mathematically consistent, even at infinite energy.
That's the goal. Qmnu achieves this because of the fractal structure. Since the dimension never collapses to a single point, it stays at GAFI 1.89, the quantum corrections driven by the Qmnu term always have enough room to operate and stabilize gravity. It naturally avoids the infinities that plague other approaches trying to merge gravity and quantum mechanics.
Okay, this fractal dimension d off 1.8928,
Yeah.
is it just about gravity and quantum information? Or does it connect elsewhere? Because if it's truly fundamental...
This is where it gets really mind-blowing. This exact same number, df log 8 over log 3, derived from the gravitational structure. It's also used within the Qmnu framework to geometrically derive the value of the electromagnetic fine structure constant, alpha EM.
Wait, alpha EM, over 137-ish, the number that governs the strength of light, electricity, magnetism. That number comes from this fractal dimension.
The theory predicts alpha EM should be approximately 1 divided by 137.036, purely from geometric considerations involving df. And that prediction perfectly matches the measured value.
But in a standard model of particle physics, alpha EM is just a number we measure and plug in. It's fundamental, but we don't know why it has that value. You're saying Qmnu derives it from space-time geometry.
Precisely. It suggests alpha EM isn't arbitrary. Its value is locked in by the fundamental fractal way space-time itself is structured at the Planck scale. It connects the universe's large-scale structure to the micro-world strength of electromagnetism through geometry alone.
That's potentially unifying in a way I hadn't anticipated.
And there's more. The theory also has a quantum fluctuation constant, gamma, which essentially weights the vacuum energy contribution in the Qmnu term. And that constant, gamma, is also derived directly from df and the calculated value of alpha EM.
So df sets alpha EM, and then df and alpha EM together set gamma.
Yes. You get this incredible cross-consistency. Gravity, geometry, electromagnetism, quantum vacuum fluctuations, all linked numerically through this one fundamental fractal dimension, df.
That internal consistency, that's a strong argument, isn't it? For the whole picture.
I think it's the strongest argument for an eternal self-similar universe. If the underlying rule, ds, holds across all these different scales and domains of physics, it points towards a system that perpetually organizes itself according to that rule without needing a distinct beginning point.
Okay, let's accept this fractal information-based non-singular universe for a moment. If there's no Big Bang singularity, what is the start of the expansion we observe? How does one cycle transition to the next if it's eternal?
The transition isn't an explosion from a point. Qmnu describes it as an entanglement-driven phase transition.
A phase transition.
Yeah.
Like water freezing or boiling.
Analogous, yes. Imagine the state before our current expansion. It wasn't infinitely dense matter, but maybe a highly entangled sort of pre-geometric state, perhaps like a 2D field of time-light quanta in massive superposition. Very high information density, but not quite spacetime as we know it.
Almost like a sea of quantum potential.
Something like that. And the trigger for the transition for the bang is that entropic gradient stress reaching a critical point, the beta term again.
So the information pressure builds up in this pre-geometric state.
Exactly. The entanglement density gets so high, the compression of information becomes unstable, according to the rule set by D. The system has to expand. The informational disorder gradient hits maximum, forcing a massive decoherence event.
Decoherence, like collapsing a quantum wave function.
On a cosmic scale, the 2D pre-geometric chaos rapidly actualizes, collapses its superposition into the expanding 3D space and 1D time that we inhabit. That phase transition driven by entropic necessity is what we perceive as the Big Bang.
So the universe kind of crystallizes itself out of a quantum information fog, driven by the need to reduce its information density.
That's a great way to put it. And it has echoes of Hawking radiation, doesn't it? Where the information properties at the black hole horizon seem to generate particle creation, here, the information properties of the pre-collapse state generate the expansion of space-time itself.
And this implies a cycle.
It seems built in. Gravity pulls things together, increasing entanglement density. That increases the entropic pressure via the Qμ term. Eventually, that pressure overcomes gravity, forcing expansion. Expansion spreads things out, reducing entanglement density, until gravity eventually dominates again on large scales, starting a slow contraction phase. Repeat.
An eternal oscillation between gravitational dominance and entropic dominance.
That's the picture Qμ paints.
Okay, but here's a practical question. If Qμ is so different, especially with these alpha and beta terms modifying gravity, why does general relativity work so incredibly well in, say, our solar system? Or for predicting gravitational lensing by galaxies? GR seems fine where gravity is relatively weak.
That's a crucial point of consistency. The Qμ corrections cannot be constant. They have to depend on the scale and the cosmic time. The theory introduces a running coupling function, specifically for the alpha term. We write it as alpha of k and z.
Alpha of kz. So k is the scale, like wave number, and z is the redshift, indicating cosmic time or epoch.
Exactly. The function looks something like a baseline value, alpha 0 times a damping factor. This factor strongly suppresses alpha at small k, large distances locally, and lets it grow at very large k, Planck-scale, or under specific cosmological conditions related to z.
So the strength of this quantum information effect, alpha, changes. It runs with scale and time.
Yes. Think of it like a dimmer switch. For everyday gravity, like planets orbiting the sun, the scale k is small, the redshift z is 0. The alpha coupling is effectively 0.
And Qμ just reduces back to standard general relativity.
Precisely. We recover GR perfectly in the regimes where we know it works. The Qμ corrections only become significant at the two extremes. The ultra-high energies near a potential singularity, or on the very largest cosmological scales, observing the universe's late-time evolution.
Ah, and that scale dependence might explain some cosmological puzzles.
It provides potential explanations for the two biggest headaches in modern cosmology, the Hubble tension and the mystery of dark matter.
Okay, let's take the Hubble tension first.
Yeah.
This is the weird disagreement, right? Measuring the universe's current expansion rate, H0, using early universe data, like the CMB, gives one value.
Around 67 or 68 kilometers per second per megaparsec.
But measuring it using local late-time objects like supernova gives a higher value.
Yeah, more like 73 or 74, and the error bars don't overlap. It's a significant tension.
So is one measurement wrong, or is the physics changing?
Qμ suggests the physics is scale and epoch dependent. Because the entanglement effects, governed by that running alpha gas, are predicted to be slightly stronger or behave differently in the later, larger-scale universe compared to the early universe.
The expansion rate itself wouldn't be constant in the way standard models assume.
Exactly. The theory naturally predicts a slight boost to the late-time expansion rate compared to extrapolations from the early universe. The framework actually calculates a predicted late-time value for H0.
And what is it?
Around 68.2 kilometers MPC.
68.2, that's right in the sweet spot, isn't it?
Mm-hmm.
Lower than the local measurements, but consistent with the CMB within errors, potentially alleviating the tension significantly.
It provides a physical reason for the discrepancy. Neither measurement needs to be wrong. They're just probing the universe at different scales and epochs where the effect of gravitational physics, according to Qμ, is slightly different.
That's neat. It avoids needing new exotic physics just for the late universe. But what about dark matter? That seems like an even bigger beast to slay.
It is. Standard cosmology absolutely requires some kind of invisible, non-interacting matter, cold dark matter, or CDM, to explain why galaxies rotate faster than they should based on their visible matter alone. The missing mass problem.
We need that extra gravity from CDM halos to hold galaxies together.
Right. But Qmnu offers an alternative. It suggests that maybe the missing mass isn't missing mass at all.
Okay, I have to push back slightly here. Isn't CDM, conceptually at least, simpler?
Right.
We just need one new particle, even if we haven't found it yet. Qμ seems to involve complex running couplings, entropic forces. Isn't that more complicated?
That's a very fair challenge. CDM is conceptually simple, yes, a particle that only interacts via gravity. But we've been looking for that particle for decades with incredibly sensitive experiments and found nothing. That's getting awkward.
True. The WMP miracle seems less miraculous now.
Right. Qmnu says. Maybe we don't need a new particle. Maybe the effect we call dark matter is actually generated by the known baryonic matter itself through its informational complexity.
How? How does the entropic stress, that beta term, mimic a giant halo of invisible matter?
Remember the entropic gradient stress, that outward push at the Planck-scale. On galactic scales, it manifests differently. The complex arrangement and high entanglement density of all the stars, gas, and dust, the baryons, generates an effective thermodynamic or entropic force structure within the galaxy.
So the information inherent in the visible matter creates an additional structural force.
That's the idea. It effectively creates an acceleration scale related to the baryonic mass distribution. This entropic structure provides the extra pull, or perhaps resistance, to flying apart needed to explain the flat rotation curves of galaxies.
Without needing any extra invisible mass.
Without needing non-baryonic CDM. And crucially, this mechanism naturally explains something called the baryonic Tully-Fisher relation.
That's the observation that a galaxy's rotation speed is very tightly correlated with its baryonic mass alone, right? Not its total mass, including dark matter.
Exactly. If dark matter were just some smooth halo, why would the rotation speed correlate so perfectly with just the clumpy baryons inside it? It's a bit puzzling in the standard CDM model, but if the structure-forming force arises from the organization and entanglement of those baryons, i.e. their entropic properties, then the correlation makes perfect sense.
Wow. Okay, that is a compelling connection. The force you need is generated by the stuff you can see because of its informational structure.
It replaces the feed for an invisible particle with a deeper understanding of gravity's connection to information.
So Qmnu potentially resolves the singularity, the Hubble tension, and offers an alternative to dark matter.
That's a lot for one theory.
It sounds too good to be true. It must be testable, right? Falsifiable.
Absolutely. If it weren't, it wouldn't be science.
Yeah.
And Qmnu makes very specific falsifiable predictions across 3 distinct experimental areas: strong gravity, laboratory quantum effects, and large-scale cosmology.
Okay, let's start with strong gravity. Black holes again.
Black hole mergers, specifically, using gravitational wave detectors like LIGO, Virgo, Qₘₙ.
When two black holes collide and merge, the final black hole rings like a bell, right? Emitting gravitational waves.
Exactly. That's the ring-down phase. And the frequencies and damping times of those waves, the quasi-normal modes or QNMs, are like the black hole's fingerprint. In standard GR, the QNMs are uniquely determined by the final black hole's mass and spin, assuming it's a Kerr black hole.
So we measure the QNMs from a merger, like that loud event GW250114 you mentioned.
Precisely. High signal-to-noise events are key. Qmnu predicts that because the entanglement correction, Qmnu, alters the spacetime geometry right near the event horizon, preventing a true singularity and forming that BHR core, the QNM frequencies, must be slightly different.
Shifted away from the pure Kerr black hole prediction.
Yes, measurably shifted. It's a subtle effect, but with enough precision, detecting that specific deviation in the QNM spectrum would be a smoking gun signature that gravity is indeed being modified by quantum informational effects near the horizon.
A ripple in spacetime telling us about quantum entanglement. Amazing. Okay, test number 2. The lab test. How do we test cosmic ideas on a tabletop?
This involves trying to directly measure the Unruh effect, which is linked to that alpha term coupling curvature and thermal energy. Experiments like LUXE light and shine in X-rays experiment are designed to accelerate electrons to incredible levels and look for the faint thermal radiation predicted by Unruh.
So LUXE tries to make empty space glow just by accelerating through it.
Essentially, yes. Now, Qμ predicts a very specific relationship that LUXE could test. Remember the unroot temperature Tu that LUXE might measure?
Yeah.
And remember the entanglement temperature Terex derived from gravity and curvature within the Qμ framework.
Right.
Qμ demands these must be consistent. It predicts that the Tx calculated from local spacetime properties, like Earth's gravity or lab-induced acceleration, should precisely match the Tu measured via unroot radiation detection.
So if LUXE measures a temperature, and that temperature matches the one Qμ calculates based on gravity and information.
That would be direct, quantifiable evidence for the fundamental link between gravity, acceleration, or quantum thermal effects that the theory is built on. It connects the lab scale to the cosmological scale.
Proof that curvature and entropy are linked in the way Qμ says.
Okay.
And the third test, back to cosmology.
Back to cosmology and that running coupling function, alpha kz.
The one that depends on scale and time.
Correct. We need to test its specific predicted effects on how the universe's structure grows over time. We do this by plugging the Qμ physics, including that specific alpha az function, into sophisticated computer simulations. Codes like CLASS or MGMBB that model the evolution of large-scale structure, LSS.
Simulating how galaxies and clusters form and distribute themselves across the cosmos.
Exactly. Then we compare the simulation results to actual maps of the universe coming from massive galaxy surveys like DZI, Dark Energy Spectroscopic Instrument, or the Euclid Space Telescope.
What specific feature are DSI and Euclid looking for that would test Qμ?
The theory predicts that the quantum entropic corrections cause a subtle, scale-dependent suppression of structure growth, particularly at very large scales over cosmic time. Basically, the entropic effects slightly counteract gravity's ability to clump matter together on the biggest scales.
So fewer giant superclusters than standard cosmology might predict, or they grow slower?
Something like that. We quantify this using statistics like F sigma 8, which measures the growth rate of structure. Qμ, via alpha K, predicts specific deviations or suppressions in F sigma 8 as a function of scale.
So if the real data from DSI and Euclid shows exactly that pattern of scale-dependent suppression,
it would be powerful confirmation of the cosmological predictions of Qμ and indirectly of the underlying scale-dependent physics and the running alpha coupling.
So it's a three-pronged attack. Black hole ringdowns, lab measurements of unroot effect, and large-scale structure patterns. If all three point towards the physics described by Qμ, especially if they align with constants derived from that fractal dimension DSI,
then the case becomes incredibly compelling. The framework would be validated, and the idea of a Big Bang singularity would effectively be replaced.
Okay, let's wrap this up. We started by looking at the biggest crack in the foundation of modern cosmology, the Big Bang singularity, a point where our physics breaks.
A mathematical signal of failure in general relativity.
And we've explored this quantum unified vacuum theorem, Qμ, as a potential solution, a theory that proposes a radical alternative.
An alternative where that singularity just never happens. It's not the universe's beginning.
Instead, Qμ paints a picture of the universe as this: eternal, self-regulating network built on quantum entanglement.
That's the synthesis, yeah. The evidence comes from multiple angles. The prediction of stable black hole remnants instead of singularities. This deep fractal structure, DFA 1.89, that seems to link gravity, geometry, and even electromagnetism, and the idea that cosmic expansion itself is driven by entropic forces. It all points towards a cyclical system, constantly balancing gravity and information, never needing that Tito starting gun.
And the core shift is profound. Gravity isn't just caused by mass and energy, but by the structure of quantum information itself. Which brings us back to entanglement, doesn't it? That famously weird aspect of quantum theory.
It really does. Which leads to a final, maybe provocative thought from this deep dive. For nearly a century, we've wrestled with entanglement through the lens of the EPR paradox.
Einstein's spooky action at a distance. Measuring one particle instantly affects its entangled partner, no matter how far away.
Exactly. And it seems spooky because we assumed information had to travel through a pre-existing space-time. But what if Qμ is right? What if space-time emerges from entanglement?
Then the non-local connection isn't spooky action through space.
It's spooky action as space. The entanglement isn't a signal traveling faster than light. The entanglement is the connection. It defines the geometric relationship, bypassing our classical notion of distance.
So the non-local correlations are just the universe showing us its fundamental connective tissue, which isn't based on classical distance at all.
Perhaps. It might mean that geometrical connection without fundamental distance is a more accurate description of reality at its deepest level. The entanglement is the proximity. Think about what that reframe's about, or about everything.